Adrian would have worked on the first version of microservices, which was known as Corba back in the day. Distributed computing.
Love course.
It's all your fault, you know. I had to write Corba apps as well. In the very early days when I was trying to build microservice systems, I came across a few talks that Adrian had done and realized that we were doing it completely wrong. So you, of course, have moved on now. Microservices are the old thing. Lambda architectures are the new thing. Take a microservice. Well, first you took an app, and then you stripped away everything, and you were left with a small endpoint, and then you strip away everything supporting the endpoint, and you're left with a function. So we're going to see how that has played out today. I know the guys at Gilt, or should I say HBC now, are using Lambda in production. I'm very interested myself to see how it works, because it's something that we're considering. I'm still hardcore microservices at the moment, so you're going to have a job to do. Okay. But without further ado, please take it away, Adrian Trenaman.
Awesome, great. Okay, so first, thank you all for coming on a Thursday night. Really appreciate it, and thanks as well to Chris. It's kind of like a race of late people, and I got back first. So I'm going to talk to you about Lambda architectures. Shout out questions along the way at any moment in time. I'm happy to take them, whenever you got them. Okay. I work for HBC, the Hudson's Bay company. That's this place here. Okay. Hudson's Bay is quite literally Hudson's Bay. It's a massive, big drainage area at the north of Canada. Okay. And the Hudson's Bay company is the company that was set up in 1670 to effectively handle all the fur trade in that entire drainage basin, which is almost 1/12 of the Earth's surface. So pretty impressive place, right? We also made it onto Netflix. Okay, there's a show about Hudson's Bay company. In this show, it is not clear whether we are the goodies or the baddies. Okay, I like to think that we come out of it looking reasonably good. Okay. Where we are today, so effectively we're e-commerce in North America and Europe as well. A lot of a mix of strong luxury brands that you would have heard of, for example, Saks, Fifth Avenue, but also as well for anybody. I don't know if there's any Canadians here, but those four stripes are to Canada what the Guinness harp and the concept of Guinness is to Ireland. Okay, every town has a Hudson's Bay. It's one of these incredible things that's kind of linked in with the culture almost. And so basically, these are all the brands that we work with. Pretty big, multi-billion-dollar. That's the e-commerce revenue per year. Pretty big. The other thing I think that makes it very interesting is that there are hundreds of stores. And stores are interesting beasts. The lion's share of our revenue still comes from physical stores. They're interesting beasts because usually when you think of e-commerce, you've got a warehouse and that's where you ship stuff from. Okay, this is like having 300 warehouses with inventory everywhere. Okay, and that creates very interesting distributed problems. Okay, so what this talk is about, it's about solving the problem of microservice dependencies with Lambda architectures. And so it attacks those key ideas there: performance, scalability, and reliability. And I'm going to talk about some Lambda architecture examples that we're kind of building out here. And I'm going to give some lessons learned as well. And of course, I'm representing on behalf of the teams here. Okay, I didn't code a lot of this stuff, but I've marveled at what's been created. Okay, when I talk about Lambda as well, I'm actually not talking about AWS Lambda, although you will see AWS Lambda in the talk. I'm talking about the Lambda architecture approach. Okay, so if you look at where our architecture has gone over time, we had a monolith, we broke it apart, we got service oriented. 2012 we got a little crazy with microservices everywhere. 2016 lots more microservices, but that's when we began to see serverless really come into play around the fringes. And then if you look at us now, where the architecture is going, really splitting up the front end at the north into multiple front ends, all using a shared set of services. This is like one of those abstract art paintings, but it's probably the quickest way to get the idea that effectively, as the architecture's evolved, we've broken it up from big, heavy things into lots of smaller, more lightweight things. Okay, so I'm very fortunate because 3 years ago at this meetup, at the inaugural Dublin Microservices meetup, the presentation I gave was, from the perspective of Gilt.com, having done a huge amount of work with microservices and having encountered what we felt were real problems. Okay, and so I did a big kind of presentation, and I talked about I/O explosion. Okay, which is in this massive microservices architecture. You call my service, I call 2 other services, they call I don't know how many other services. There's an I/O explosion of services calling services, a mishmash that goes out of control. And it's very easy then for one service that's probably not even kind of mission critical to actually take out potentially something in a very, very odd way. So and back at the time, we're looking to this thing called Lambda architecture for critical path APIs and real-time updates of information and order one lookup. Wow, order one. Okay, that effectively, when you want to get a piece of data, you can get it back instantly. Okay, and it kind of moves services from things that depend on other services to things that are entirely self-contained, fast, highly available, and always there for you. Okay, so I'll talk briefly about Lambda architecture, the Hollywood principle. Okay, so basically, Lambda architecture is really about making batch processing sexy. Okay, often when you hear of Lambda architecture, you hear about a bunch of other really kind of cool tech, but ultimately I think the idea is very, very simple. Okay, what you've got is some kind of data source, and it is the source of truth, the single source of truth. So for example, your user data or your product data, it's in this database over here. And what you want to do is get a view of the data over here. Okay, and usually you want that because you have different kind of requirements out of the way you access that data. Lower latency, it has to be super fast. Maybe you want the data in a different shape or aggregated with something else. Or maybe you're going to do some kind of long, highly complex queries and you don't want to touch the operational database. So the key idea is how do you replicate that data across? Well, you have this idea of the batch, right? The big snapshot that you chuck over here, call that the baseline, and then you've got stream processing in real time. Now, as you can see here, what is a stream? This idea of a stream is really fascinating to me because it's something that I always knew about from a programming perspective, but not from a system perspective until the last few years. Whenever I thought of sending messages, I thought of queues or topics in the old JMS parlance. We never had this idea of a stream. What is a stream? It's an append-only, immutable log store of interesting events. Okay, so you just push data to the stream, and the stream gets infinitely big over an infinitely large amount of time, and it never forgets. It's always got information. The nice property there is that you've got like a cursor to a point on the stream, and effectively then you can replay from that point or any point in time. Okay, so this is kind of the core idea. Here's an example of a bunch of data that we have, and the T's there are kind of like things that happen at a particular moment in time. There's there's 5 bits of data that went on the line. Okay, and then effectively you pushed over that big batch, and then something new happened at T6. So at T6 we've got Dipsy, we've got this other new piece of information coming through. Okay. Later, we're going to have the next snapshot that happens is going to contain the full data set. Okay, and as you can see, then T7 something happens, and T8 something happens as well. Okay, so you're always getting a massive big chunk of data, and then you're replaying events. Okay, if ever, there's a really nice property here. If ever you need to rebuild that view of the data, all you have to do is get the latest batch, okay, and then replay all of the events since the longest time. So that green line there, we take that batch T1 to T6, and then we go. Let's just point the our cursor to T6, which is the latest timestamp I got here, and then I'm just going to replay, okay. And that's a very, very quick way to completely reassemble my view on the right-hand side. Okay, everybody with me? Seem reasonable? Yeah, okay, nothing too crazy there. It's an inversion of control, like the Hollywood principle. Don't call us, we'll call you. And this is, I think, the interesting part that makes it amenable to these order one lookups, okay? So Previously, if I needed a view of the data, and this is in my Gilt 2016 microservices world, if you wanted data from me, I would go, okay, I'll get you the data, and every call you make on me, I would make on this fellow on the left, okay? We had this massive dependency of services against services against services, okay? And really what we've done conceptually is we've said, this source of data here is going to push changes over here, okay? And that nice property means is that this is always up to date, okay? Which means you can serve the data next to instantly. And that's the key idea. So let's talk then about caching, okay? And how Lambda architecture helped us out. Okay, and this applies directly to the problem of Gilt.com, okay? For those of you who don't know Gilt, we source luxury items, expensive shoes, dresses, handbags, etc. We shoot them, we make them look good, so we get them direct from the brands, we make them look great. We have our own warehouses, we do all that kind of work ourselves in terms of the code, and then we put it up on our website, and we sell every day at noon. So what happens is all of that stuff, that low quantities of high value inventory goes live at noon, okay? And the idea then is, this is what our customers look like, a massive stampede of customers trying to get that highly discounted luxury product, okay? So here's what our customers really look like. This is 1700 GMT, which is noon New York time, and you can see that's a typical profile on our network load balancers. Okay, so what's the problem? Massive pulse of traffic, right? A big drive of traffic. We want to be able to serve fast. There are low inventory quantities of high value merchandise, and it's all changing rapidly, so you just can't cache, okay? Or caches go out of date, okay? You need to serve as fast as you can. And then individually personalized landing experiences, again, you can't cache, okay? So, caching, woo, okay? The rule we basically came up with was just say no, right? Caching is possibly the thing that you jump on as, okay, that'll answer it for us. And what we used to find then was it created more problems than not because there were caches everywhere, okay? So you just say no, right, until you have to say yes, okay? And then you try and just say maybe. We really try and stay away from caching, from standard caching approaches as often as possible. So let me tell you a story. So here's a stateless cache-free library busted. So this is a bunch of services, product, inventory, and service. This is one of our, it's a product detail page. It's a Play app that serves product details over the web, okay? And what we did was we built a really beautiful library in Scala called Commons. And what that did was it hid away all the vagaries and all the rubbishy APIs that evolved over time here and gave a really beautiful, strongly typed, gorgeous Scala API. Fantastic, okay. Now, so the idea was that the app would then use all those services through Commons lib, okay? And what we discovered, though, of course, is like any developer is going to go, oh my God, I can't believe I have to pick up the product every time. Why don't I store it in a cache, okay? So what used to happen was, and I'm guilty, I built these, you build a brand cache because you don't want to go every time you want to look up Gucci, make a remote call. You're going to store it locally. Okay, and the same with products, right? So the problem then was we had every web app had arbitrary caching policies and ideas that were developed by whatever team owned the app. The search app had a different thing, the listing app, the homepage app, kind of got a bit messy. So we had this bright idea. Why don't we move the caches into this library? That will be awesome, right? And that's what we did, and we thought we were great. Okay, we thought that we'd gotten to that maybe moment, and we figured we should put the caches in there. Okay, so what we did was we pushed caches in here for our brands and products, and we said it's going to be a 20-minute cache refresh. So we'll always kind of purge through every 20 minutes. So and it worked very well. It worked very well until the business changed its mind about something. We used to only sell a subset of our product every day, the sexy product that we had that was new, okay? And then the business decided, well, we worked on it with them, why don't we just try and sell everything we possibly have in the warehouse? Let's make it available and let's just sell it, okay? So those caches that once were small, lightweight, and well-behaved, they all went absolutely crazy, right? Define crazy. Orders of magnitude more SKUs. So the JSON that we got back from product service was 1 gigabyte, okay? Now, when all the instances of all the parts of your front end are all making this call every 20 minutes to get a gigabyte of JSON, it's just like, holy crap, okay? The startup time of the services to warm up the caches was greater than 10 minutes. This meant that rollouts that should have been simple in the past, all of a sudden were taking hours, okay, instead of minutes or seconds, okay? There was a JVM garbage collection every 20 minutes on the cache clear. And the garbage collection was extremely high because you get all that JSON back, and parsing JSON creates tons and tons of objects, and then all of a sudden, you know, the JVM goes crazy. Okay. Also as well, it took over an hour to propagate a change. So for example, a change like, oh my God, you've spelled Gucci with a K, right? And the merchants are going crazy, and how do you actually, you know, update that brand information? And effectively, you know, it just takes ages to propagate, okay? And then typically we were running on things like M4X larges with 14 gig JVM heaps, okay? So it was like we kind of fell into a bad place. Okay, so what are we doing? So here's how we came around that problem. So this is our source of truth with all our product data, okay? It's Postgres. And effectively what we did then was we built a kind of a timer that says, do you know what, I'm going to take all that really interesting information and I'm going to take it and I'm going to dump it onto S3, okay? I'm basically going to take a big load, and this is my snapshot, okay? And then what I'm going to do is my product service now is going to pull off S3, and it's going to dump all that data into Elasticache, okay? This is my batch, okay? Now, of course, as we said earlier, these big S3 files, we know the last timestamp change of every single piece of information. So that means, you know, we can upload everything to here. We have this secondary service here called Calatrava, which we've always threatened to open source. We haven't open sourced yet. And what it does is it just listens for changes on these tables and publishes them to a Kinesis stream, okay? So this is the batch. This is the Lambda events here that are kind of saying, here's the little changes, okay? The top part is the real-time part, okay? Effectively then, we ended up then with this sort of like commons library hitting off Elasticache, okay? And that's your order one. You know, you're saying, give me this product, and you give the ID, and then boom, it's straight back at you. Elasticache is super fast, okay? So what happened? Okay, so we ended up then with real-time propagation, order and lookup. We used a proper service to do the caching rather than our own. The other thing is we did end up putting a very, very small L1 cache in the in common still. But the impact that we got out of this was a startup time of 1 second. Okay, so this is amazing. We're now at a point where we don't have to wait all that time. Okay, there's no more stop the world garbage collection. It takes seconds to propagate a change now because the change gets picked up here, blasted onto Kinesis, and then boom, it's straight through. So we have no problem with changes anymore. We're still using 4x large in terms of machines, okay? But there's no more stop the world garbage collection, okay, which is great. Sorry, I said that there. Yeah, sorry, we're X large, 6 gigabits JVM heap, right? So we brought down our heap. We don't need that much memory anymore. That's great, okay? But there has been a trade-off. You see, the problem was we're still doing all of that JSON marshalling between Elasticache and here, and that's why we need the high CPU. So, what happens? I guess, you know, next steps there would be actually to say for a service like this, actually use Avro rather than JSON, or use Corba. Sorry, I couldn't resist it, because it's way better than everything else. Okay, wonderful. Right, so Calatrava, github.com/Gilt, well, soon be public. That was the tool that did the small deltas. All right, I'm going to blitz through some of this. Okay, so what I showed you there was this interesting thing of we are taking the data and we're taking a batch and we're pushing through. Okay, the deltas. Here, something similar, in that, although it is a variant, and it's an important variant, because you start off with something simple, and then you discover that actually things are a little harder. So we had a similar problem in terms of saying, I wonder if we had, how do we build a search index? You've got product service basically reading off this source of truth, and you've got some kind of search indexer, which is taking that information and putting it into Solr. Okay. So the problem here, the polling service means changes to product data are not actually reflected in real time. So the search index isn't getting updated in time. So how did we deal with this? Okay, here's what it looks like. So we had brands, product, sales, and channels all getting pushed through to S3 as per previously. Okay, we had Caltrava pushing the deltas previously as well. Okay, but the problem that we had is this. If you change a brand, okay, you think about on the left-hand side, we've highly normalized data. It's database tables, okay? On the right-hand side, if you look at Solr, it's a document, denormalized data source, right? What happens is the arity between your entities matters, okay? So every product has a brand name, okay? If you update the brand name for Gucci, okay, then you've got to go through, let's say, 1,200 products and update their brand names, okay? And if you don't do that, the search index is not going to work, okay? So what we ended up having to do was say, let's actually pull that information together here and, snapshot of deltas and actually reassemble a relational view of truth on the right-hand side, okay? In other words, we're going to have to store it in a denormalized form and make sure that if there is a brand change, we're going to make all the updates down here, okay? And that gives us the control then to then say, well, now that there's been a change of 12,000 or 1,200 things in the view of truth on the right-hand side, that's the point then where we can now push out those documents into Solr and do a real-time update, okay? So we moved from a situation in Solr of doing like really, really big Solr indexes to actually moving to a highly real-time version, okay? But we did have to build all these kind of complex pieces, okay? And that's kind of like an interesting kind of, we're having to build quite a lot here, okay? There's the benefits there. Changes in real time. Rebuild of our index is super fast. We have the same logic for the batch as for the stream, which is kind of nice. But this interesting problem, we still needed to have a relational database to solve what was ultimately a relational problem, okay? Okay, part 3, okay. So this one is probably the hardest. This is the one that will tax your brains most, okay? And then we should have an easy landing through some of the last kind of bits of material, okay? What I've shown you so far is a read-only use case, okay? It's like there's stuff in this source of truth, and I've got a search index, or I've got services that are just reading, okay? And what we wanted to say was, well, what about a situation where you're looking for high performance, but you're doing reading and writing? How does that look? Okay, so stay with me for this one. Here's my problem. My problem is I've got tons of stores, okay, and I've got a warehouse, like a physical warehouse, and I've got OMS. OMS is pretty much an industry standard. It's not a standard, it's an IBM product called Sterling OMS. It's an order management system. Typically, it manages your order life cycle and also your inventory counts. Okay, that's what I have on the left, okay? On the right, I've got the internet. And the problem here is that the internet moves fast with massive throughput and lots of people trying to get inventory. The problem on the left is that this is kind of like an app server sitting in the back office. You just can't hit this with internet traffic, okay? So you got a real classic problem here of this is a really solid way to store your inventory, but it won't work for internet use cases, okay? So what did we do? What did we put in the middle of this so that we can read the latest inventory counts and know how much product we have? And then reserve inventory, right? I'm interested in this product, I want to buy it, okay? And that lowers the inventory count because I've bought it. Okay, here we go. First thing, OMS very kindly gives real-time availability, and that's called RTAM, real-time availability messages. We put that onto a Kinesis stream. And what we have is a guarantee that every SKU will pass through this every 24 hours. So we'll always know within a day what OMS thinks the truth is. Okay, that's nice. We have a little Lambda, and bashes that into Elasticache. Okay, so that's really, really nice. Okay, we've now got, as you can imagine, Elasticache will serve all of our internet traffic, so that's going to be really, really great. And then we've got our Scala, whatever, API in front of that, so that gives us a really beautiful RESTful API. Now, what's also interesting about this in terms of pushing the data out, and it's changed the way we think about lots of our services. Usually you write a service and it's like a RESTful service, and people request things of you and you give it to them, okay? Here, what we're doing is we're making available Kinesis streams that any team can listen on. So any team that's interested in the fact that inventory's changed can just listen on that stream. And then they get pushed the data on demand. That's kind of nice. Okay, so let's have a look at what happens then when we want to do a reservation. So somebody calls this RESTful API and they say, I want to reserve that dress, okay? So what we do is we hit Elasticache, okay, and then and we kind of say, hey, is there any inventory available, okay? Then number two, we hit OMS and we go, great, let's reserve it, okay? Now, when we make that reservation, and the interesting part about this reservation here is that, actually I'll tell you in a second. Okay, so let's imagine that OMS was there and we reserved the item, okay? We then put onto that stream a change event, okay? There was 7 items, now there should only be 6 because I reserved one of them, okay? We write that into Elasticache, okay? And then we're good, okay? The last part then is the Lambda event there sends to another Lambda, which sends back to OMS a clarification that this is now a reservation that has been made, okay? And that effectively then becomes the overall loop, right? So, so just again, the approach, number 1, is the inventory greater than 0? Number 2, attempt a reservation. If it fails, generate a random reservation ID. And this is really important, if it fails, because OMS may not be available at any moment in time. Put the change in the RTAM stream, update the cache, and then trigger a best effort to true up inventory in the latter stage here, okay? There's a lot of stuff there. I don't expect you to grok all of this in one moment, okay? What is stunning about this as a design, and I really, it took me a while to kind of get into it, is in this design, even on failure, right, there is only one way through the system, okay? If OMS is there or if it is not there, okay, the route of that reservation is the same no matter what. And I think as a design choice, usually you could be tempted to say, okay, I'm going to try something, and if it works, I'll put it onto this Kinesis stream, and if it doesn't work, I'll put an error on this Kinesis stream. And this approach, actually, it's always the same thing, and that's highly predictable, all right? Every fork you take in a complex system like this gives you multiple possibilities and makes it very, very hard. So this fact that there is only one path through the system is really important. Okay, part 4, in which we consider Kafka versus Kinesis. And I believe our pizzas are on the way soon, so let's see how we get on here. Infinity. If you remember at the start, I kind of sold you a pipe dream. I said that a stream is an immutable, infinitely long history of all the interesting things that happened. Okay, and that sounds great, except obviously it doesn't exist. Okay, it's kind of a conceptual computer sciencey thing. It isn't really. If you look at Kinesis, I think their default retention policy is 1 day you can pay more money for a week. Okay, but ultimately your stream is going to forget things. And that's why I have to add, we have to have all of these snapshots built into the architecture, okay? We need this concept of the snapshot, okay? And so there comes this incredibly, what sounds like a really boring feature called log compaction, okay? Log compaction is a very, very interesting property. It sounds like, you know, I'm going to zip up your log4j file when it gets big, right? That's not what it is. It's this amazing idea, and I'll just talk about it very quickly. And it's something that Kafka supports outside the box, or out of the box. So effectively, log compaction says, whenever you send me an event, I'll always remember the last interesting thing you said about an entity, okay? Let's have a look at this. Superheroes, James Bond. These are data that's coming through, so we write it onto a queue, or sorry, onto a stream, Kafka stream. 2, Doctor Who, we write it on there, okay? 3, James Bond. This is an update to the interesting entity that is James Bond. We spelt his name incorrectly, okay? What happens here then is Kafka will go, okay, I have a new value for that one. Father Ted comes along, a little bit out of character, so Father Ted goes in. And then later, Kafka will just delete the old value, okay? It's not important. This is what log compaction kind of gives you. We'll save the most interesting things about the last most interesting thing about the entity, okay? And this gets exciting because you end up with this property, which sounds like something out of Star Trek, which is table stream duality, okay? Over time, the information that was in your database at the start, the one on the left, the source of truth, and the data that's on your stream is actually, it's all there, right? For all intents and purposes, the information is in both places, okay? And that's then this amazing property, because that means if you have table stream duality, you don't need snapshots anymore. And you can get rid of all that stuff about taking snapshots into S3, and you can simply say, I've got all the stuff on the stream, okay? And that's, I believe, called a Kappa architecture, which is sort of like, you know, when you've left Lambda behind in the dust, this is what you end up with. So there's lots of amazing things, you know, about the ecosystem of Kafka. So we started everything and we were talking about Kinesis all the time. And Kinesis has these very simple stream primitives. When we look at Kafka, there's a whole ecosystem of kind of cool toys to play with, okay? So this is an example here, right, from Fabrizio. And this is an example of why the Kafka ecosystem is so awesome, right? It is like, imagine taking 2 streams, okay, and joining them to one, right? So here's a stream here, the product table. Well, that's a stream of all the product information that I got over time. The inventory table, that's a stream of all the inventory events that I ever got, okay? And effectively, we're going to product table.join with the inventory to create a stream called product inventory. Oh my God, my products are enriched with inventory. And this is like virtually, this is just a stream now that I can read from at any moment in time, okay? Mind blown. If you think about how hard that would be to kind of get that logic, and the fact that we can actually just say, yeah, why don't we just merge streams? That's just amazing, okay? That's only a fragment of the code, lines 3 to 17 of the snapshot that I had. There was a little bit more code around that, but I think it captures the idea really, really elegantly. There are things that you can do with Kafka that Kinesis just doesn't kind of give you out of the box, right? So what do we learn? What did we learn? Okay, let's have a look at what we learned. Item 0. You can apply a Lambda architecture to create highly scalable, reliable offline systems, okay? When I say offline systems, I mean where you're able to get data even if the source of the data is no longer there, okay? And that's actually, you know, a very desirable property at internet scale. Number 1, I'm doing computer science counting here. So number 1, replicate and transform the one source of truth. This was a little bit of an eye-opener for me, because I think when we started the microservices kind of work, we always said, let's just store the data in one place only. Products, they're in that database. Users, they're in that database. Inventories over here, okay? There was only ever one source of truth. And that appeals to your software engineering 101, do not repeat yourself, only write the code once, only store the data in one place. It appeals to that. But actually what we learned is you should have one source of truth, but it's okay to have multiple views of truth. as long as you have real-time updates. Okay, and so that was a really big learning for us. Okay, number 2, it's not all unicorns and rainbows. As you saw, we started off with a simple problem, which was like a snapshot and a stream, and it felt good. But then we were like, the harder problem for search meant that we had to introduce a secondary relational database along the way. Okay, so it's like the easy problems are like hello world in any language. It's like, wow, that was breathtakingly easy. But the slightly more complex problems all of a sudden get hard. Okay, and you end up having to build in that complexity into your solutions. Okay, so that was like a big learning for us architecturally. And then finally, I think that the way we've landed on it is that in terms of choosing a stream technology, Kinesis is like the no-brainer thing to adopt. Okay, Kinesis is easy peasy, and if you're on Amazon already, you're just right-clicking and you're throwing a whole bunch of stuff up, and it's just done. It's dead easy. It's great. Okay, and we started with Kinesis, and we've used it extensively. The thing is, though, we're now seeing the more complexity and the richer feature set of Kafka suggests that's a much better architecture for us to be using than Kinesis. So it's like you start off with your basic primitives over here, and then you upgrade to Kafka. That's kind of where we've landed right now. We're at this phase right now where we're saying we're going to take on Kafka. Now, Kafka is not like an easy ride. You've got to run those things yourself. There's no like easy out-of-the-box Amazon service that puts up a Kafka cluster for you. You've got to invest something of yourselves in it. We're starting that pathway now on some teams, and so we're very, very keen to see how that all works out. Okay, so pizza's here, which is great. I can happily take any questions, or you can take questions during pizza. Okay. Actually, you should say there, Fabrizio is over there. Say hi, everyone. Say hi. There we go. Fabrizio is one of the brainchildren of a lot of this work. So it's an honor to be able to get to present his stuff. Right. I'm probably 70% accurate in my architectural diagrams, kind of. I'm sure there's some skeletons buried there, and some simplifications, but this guy's really the master. Okay, do you want to take a question or question? Yeah, great.
I'm definitely going to throw one at you.
Okay.
One problem that I'm working with at the moment is propagation of complex permissions. So imagine GitHub.
Yeah.
Permissions model where you have projects and users and organizations and groups and different activities, that type of stuff. And you want to have one source of truth, a permission store of some kind that applies rules, etc. And we would have gone straight for there's just one service, you cache the permissions, and then you have cache and validation and do that. Is this a suitable architecture to use where don't call us, we'll call you?
It's a good question. So
bear in mind the downside of the wrong permissions is much higher than the downside of missing a product.
so that's actually kind of interesting. I was going to say that permissions don't change very often. Okay.
But when they do, they need to update.
So if it's the case that when they do, they need to update, then I don't think you have a choice. I think you do have to kind of say, well, how do we make it so that the propagation goes as fast as humanly possible? Okay, and obviously you really are. I mean, you're not going to get instantaneous, but you would want it to be in seconds, perhaps. So I guess the use case is if you were, changing some perms and you want to block somebody out, you need within seconds or within like a blink of an eye time anyway, to shut them out. So I would say yes, right. That does feel like an interesting use case. I think that in that case. It's interesting. Do you need a snapshot or not is the question. I think you probably do because you want to, that's interesting. I don't know.
And you need audit trails, so you can't come back to logs.
That's actually another interesting thing. But I think that if you're going to have an audit trail, I don't think the stream concept is the right concept for an audit trail. Because certainly the idea of a long-running immutable audit log, that's what you want to build, right? A big table in an RDS database would probably do it for you, right? I wouldn't store it in a stream because conceptually streams are ephemeral, or sorry, they're eternal, but actually they're not. So, but yeah, I guess, yeah, definitely latching onto the real-time side for sure, yeah. Okay, cool, yeah.
Part question, part statement, I guess. You mentioned at the end about Kafka, like not kind of being up on AWS, but there are managed Kafka services, right? You look at those and why do you reject
So
them?
we haven't looked at managed Kafka services right now, right? And I think it may simply be timing. You know, we just haven't got around to it, right? I think as well, there's an element of kind of we started with Kafka about 2 years ago. Got very excited, and they were like, "Oh God, it's just our engineers saying this is a pain. Like if I use Kafka and I run my own instance, then I have to set up with PagerDuty, and then I'm on the hook for it. It's much better to just have somebody else's service." So, out of sheer frictionless ease of use, we adopted a whole bunch of Kinesis. Okay, and we kind of like left Kafka for dust, and now it's like you almost see the whole kind of tech market kind of going, actually, do you know what, this Kafka thing is really good. It's worth its weight. Yeah. Cool. Any more questions? Yeah.
Do you ever foresee a situation where you dump large size and just use Kafka for everything?
That's what we're getting to. Excuse me. So if we look at the original architecture that we have for our search, okay, that architecture is predicated on all that older technology. Okay, so now we look at Kafka, K-streams, K-tables, and all of a sudden it's like, ooh, we don't need that anymore. And that's exactly what log compaction gives you, right? And I think, you know, I was speaking at the Dublin AWS meetup. You know, I kind of feel that Amazon needs to step up and create log compaction for Kinesis, or it's going to lose all this traffic. Because once you start going beyond the initial use cases and try and start doing this stuff, you do end up building complexity, right? So, yeah, cool. All right, let's get pizza before it gets cold, and I'm around and I'll happily answer questions and everything. So thank you very much. All right.